In this investigation, we formalize the key aspects of proportional relationships using graphs, formulas, and tables to represent how the values of proportional quantities change together. Recall the context where a hotel is repainting all of its guest rooms. The painters needed 11 gallons of paint to repaint the first 4 rooms. If we assume that this relationship holds no matter how many rooms are painted, then there is a proportional relationship between the volume of paint used in gallons and the number of rooms painted. First, let's take a moment to identify the quantities and determine if they are fixed or varying. The number of gallons of paint used is a varying quantity as we imagine painting more or fewer rooms. Similarly, the number of rooms painted so far is a varying quantity as the painters work. The total number of rooms and the total volume of paint used to complete the job are fixed quantities, although we don't know what their values are. Finally, we are assuming that there is a constant ratio of the number of gallons of paint used to the number of rooms painted, so this is a fixed quantity. Let's visualize the values of the varying quantities using line segments. One line segment's length represents the number of gallons of paint used so far. The other line segment's length represents the number of rooms painted. By putting these line segments next to each other, we can emphasize that the number of gallons of paint used is 2.75 times as large as the number of rooms painted. We can also simulate varying the values together to maintain this relationship. No matter how many rooms have been painted, the number of gallons of paint used is always 2.75 times as large. When we turn one of the line segments and join their starting points, we can use a point to simultaneously represent the values of both quantities at the same time. Here, the vertical axis will represent the number of gallons of paint used, and the horizontal axis will represent the number of rooms painted. Each point represents a specific number of rooms painted and the number of gallons of paint needed to paint those rooms. The specific pairs of values we see on the graph, represented as points, can also be represented in a table. For example, the points 2, 5.5, 5, 13.75, and 7.5, 20.625 are on the graph, and we can represent these pairs of values in a table. Finally, we can define variables to represent the values of varying quantities in the situation. Once we do this, we can write a formula to express the relationship between these values. Let R represent the number of rooms painted, and let P represent the number of gallons of paint used. The ratio of the number of gallons of paint to the number of rooms painted always has a value of 2.75 as they vary together, so we can write P divided by R equals 2.75. Since this also means that the value of P is always 2.75 times as large as the value of R, we can also write P equals 2.75 times R, which is a formula that expresses P in terms of R. Note how this formula could be used to produce or check values in the table. For example, the pair 7.5, 20.625 is in the table. If we plug these values into the formula P equals 2.75 times R, we see that the formula validates this pair of values, since 20.625 is indeed equal to 2.75 times 7.5. On the other hand, if R equals 3.3, then P equals 2.75 times 3.3, which equals 9.075. So the pair 3.3, 9.075 could be added to the table. In addition, the formula simultaneously represents all possible pairs of corresponding values for the number of rooms painted and the number of gallons of paint used, just like the graph. When we choose specific values that make the formula true, it's like choosing specific points on the graph. We are just looking at specific examples from the full set of possible solutions. For example, the point 7, 19.25 is on the graph of p in terms of r, and this pair of values is a solution to the formula relating p and r. On the other hand, the formula tells us that when r equals 3.3, p equals 9.075, and hence the point 3.3, 9.075 is on the graph of p in terms of r.